Hey, good morning, everybody. This is Sean Downs, Sean for Science, and today is an extremely windy day to be studying mathematics, so today we're indoors. Recently, we've been talking about representations of SU2, and we have explicitly constructed a two-dimensional representation of SU2 using anti-commutating kind of Grassmann variables theta plus and theta minus, whose action in terms of the Li algebra was given by the map j plus or minus gives us theta plus or minus, and j3 is theta plus, theta minus, minus 1/2. We saw that this representation was given basically by the span of two elements, 1 and theta plus, or v0, v1, which essentially form the L equals 1 irreducible representation of SU2. Today, we're going to build the rest of the irreducible representations of SU2 explicitly in terms of tensor products of this two-dimensional representation with itself. So to that end, let's do a quick informal review of the highlights of tensor products. In a past video, we talked about tensor products in terms of modules over some rings, but today we're going to be using something a little less restrictive. That is to say, we're going to be considering the tensor product of two vector spaces over a commutative field. So let A and B be two vector spaces, that is to say two representations of the Lie group G, defined over some commutative field F. The tensor product of A times B is essentially the Cartesian product of A times B, quotiented by some particular set of elements that are pretty intuitive to discuss. So rather than talk about any kind of universal mapping property, I'll just informally say here that if you consider an element little a times little b in the tensor product of A times B, we want to make sure that we're identifying items that are like, for lambda in F, lambda times little a times b need to be identified with a times lambda of b. So in other words, that lambda needs to be able to act kind of mindlessly across both factors of the tensor product. And so from this, it's pretty easy to see that the tensor product A times B is also a vector space over F. So since A and B are representations of some Lie group G, you might ask, what is the action of G on the tensor product of A times B? Well, that turns out to be pretty straightforward, so let G be some element of the Lie group. The action of G on some element of the tensor product A times B is given by simply G on A times G on B. Now, it is true that not all elements of the tensor product can be written in a neatly factorized way, like A times B, but it is true that any element of the tensor product can be written as a sum of such terms, and so the action of G in defined this way is well defined over the entire tensor product. Of particular importance to us today is going to be the action of the Li algebra on the representation, and to that end we need to recall that the Li algebra, say Fraktur G of the Lie group G, is kind of like the tangent space to G. If you think about it as a manifold, suffice it to say, elements of the Lie algebra could be thought of as kind of infinitesimal group transformations. So for some element H in the Lie algebra, there is some element in the Lie group near the identity, say G sub H, given by 1 plus epsilon H plus order epsilon squared in higher terms, where epsilon is a number that's really, really small, and we're going to understand that we're going to be taking it to 0 at the end of whatever calculations we're doing. So from that perspective, it's pretty easy to see that the action of GH on the tensor product A times B is given by A times B plus H on A times B plus A times H on B. In other words, the Lie algebra acts as a derivation on the tensor product A times B. Awesome. Let's now specialize to the case where G is equal to SU2 and A and B are both the same vector space, the two-dimensional explicit representation of SU2 we've been discussing so far. To that end, you might recall the L parameterization of all the irreducible unitary representations of SU2, which were given in terms of this wedge in the parameter space that were essentially eigenvalues of the quadratic Casimir operator Q and kind of the Cartan subalgebra diagonal element J3. And we labeled the different representations by a natural number L, so L0, L1, L2, L3, and we've already discussed L1 in depth, so what we're going to be doing now is be considering higher values of L. So to that end, let's name the representation, the Lth representation of SU2, the explicit one, as VL plus 1. And as we'll see, the dimension of V, L plus 1, is going to be L plus 1. So in particular, V2 is the representation that we've been considering so far. So our big claim for today is that the tensor product of V2 times V2 is going to be a reducible representation of SU2. Specifically, it's going to be the direct sum of two irreducible representations of SU2, namely V3 and V1. Proof. Recall that V2 is given by the span of two orthonormal elements, V0 and V1. So the tensor product of V2 times V2 is given by the span of the products V0 times V0, V1 times V0, V0 times V1, and V1 times V1. To get a feel for how these items behave, let's act with J plus on V0 times V0. Recalling that the Li algebra acts as a derivation on the tensor product of V2 times itself, we find J plus on V0 times V0 is given by the sum of V0 times V1 plus V1 times V0. Now, since V0 and V1 are normalized, it's clear that the action of J plus on V0 times V0 is not. So we can fix that by kind of redefining or rescaling the operator J plus on this tensor product space by 1 over the square root of 2 times theta plus. So from that perspective, now we see that J plus acting on V0 times V0 gives us 1 over the square root 2 V0 times V1 plus V1 times V0. Note also that we can act again by J plus on this element, and we find that, recalling, of course, that J plus on V1 vanishes, there's only really two non-vanishing slots here that we can compute. And so finally, we see that J plus on V0 times V0 gives us V1 times V1. And now hopefully you see why that normalization factor was useful. So indeed, define the three elements W0, W1, and W2 by... So here I'm going to leave two things for you kind of as an easy exercise. The first is that J plus on W2 is 0, and J minus on W0 is also 0. And secondly, that these W's form an orthonormal basis for a subspace, so let's call it V, of the tensor product V2 times V2. Right, so V, the span of the W's, is not quite the full tensor product V2 times V2. There's kind of one orthogonal dimension missing. So to that end, let's define M1, given by 1 by the square root 2, V1 times V0, minus V0 times V1. Since V0 and V1 are orthogonal, it's pretty clear to see that W1 and M1 are also orthogonal. And so indeed, the tensor product V2 times V2 can be written in terms of V plus the span of M1. So at this point, if we can show that V is equal to V3, and the span of M1 is equal to V1, we'd be done. So let's go ahead and do that. The action of the operator J3 on M1 is given by, which, as you can see, individual terms vanish, thereby giving us a M eigenvalue of 0. The action of Q on M1 is given by, which you can see again, because of the minus sign in between the two terms, gives us also 0. And so clearly the span of M1, that one-dimensional subspace, lives on our wedge of irreducible representations right at the bottom vertex. In other words, yeah, the span of M1 is in fact the trivial representation of SU2, that is to say, V1. Great, so it remains to show that V is given by V3. So to that end, we're going to play the same trick, so let's act on W0, W1, and W2 with J3, and we find, well, the action of J3 on W0 is pretty easy. That's minus 1/2, which is minus 1. And on W2 is also pretty easy. That's plus 1/2, plus 1/2, 1. Great. And so finally, the action of J3 on W1 is given by, and once again, the two individual terms cancel independently. And so we find that the M eigenvalues are minus 1, 0, and 1, which should get us somewhat excited as we recall that all representations of SU2 differ by integral units of M. Now, since Q and J plus commute, it suffices to consider the action of the quadratic Casimir Q on W0. And again, since J minus on W0 is 0, we see that this reduces to the action of basically J3, which we've already computed, and so we find that Q on W0 is 2. And so indeed, given that we have eigenvalue q equals 2 and eigenvalues m given by -1, 0, and 1, we see that in fact, yes, V is the three-dimensional representation, irreducible representation of SU2 up here in the wedge. So yes, V is V3. And so we're done. While it is the case that arbitrary tensor products of factors like V2 do not give irreducible representations, and you have to kind of be worried about the combinatorics of how the individual irreducible representations appear in terms of the decomposition of that reducible representation. This construction has given us kind of an inspiration for how to go about constructing the Lth irreducible representation of SU2. In other words, we start with the symmetric product of V0s, right? So let's go ahead and construct the Lth SU2 irreducible representation, which we'll call VL plus 1, by considering essentially J plus acting on this element L sub 0 given by L copies of V0. Now, I'll just kind of summarize a bit of the information here. So hopefully it's pretty clear that J minus on L0 is 0. And that J3 acting on L0 is L times -1/2. You might also expect there to be the element L sub L given by L copies of V1 times itself, and J3 acting on such a state would give us an eigenvalue L over 2. So finally, one more fun fact is that Q acting on L0 is again essentially amounts to J3's acting on L0, which we've already computed, and we know that the eigenvalue little q is going to be given by L over 2 times the quantity L over 2 plus 1, which has all of the right eigenvalues associated to the Lth layer, if you like, of the wedge of irreducible representations. So to kind of finish this construction, I'll leave it to you as an exercise to prove that the span of L0 and J plus on L0 and J plus on L0 all the way out to J plus to the Lth power on L0 gives us V L plus 1. And to do that, you might consider two hints, if you like. The first hint is, of course, that J plus to the Lth power on L0 is going to give us L sub L, right? V1 times V1 all the way out. And the second hint is to evaluate the commutator of J3 with J plus to the mth power for some integer m. Suffice it to say, you're always going to find kind of the VL plus 1 representation of SU2 latent in an L-fold product. But that leaves you with a, 2 to the L minus quantity L plus 1 dimensions that you have to kind of redistribute in terms of the other irreducible representations of SU2. So the combinatorial technology for dealing with this is called Young tableau. I'm not going to get into the details of Young tableau here other than to maybe point out the fact that you're just stacking boxes and there's rules for how those boxes stack, and those rules are related to symmetrizing or anti-symmetrizing representations together. And for fun, I'll give you some of the basic constructions here. So we've already seen V2 times V2, but you might have V2 times V2 times V2, and V2 times V2 times V2 times V2. And why not V2 times V2 times V2 times V2 times V2 in terms of all these. So yeah, there's a lot of numbers to keep track of, but it's still it gets pretty easy once you get used to the mnemonics. And hopefully from all the examples that I've just presented to you today, you can divine what those examples are. Okay, so that's all for today. Hopefully that wasn't too long. I'll do some short ones coming out soon. So anyway, have a great day. Go outside. It's nice. It's spring. See you next time.